This virtual field trip is focused on the fault damage zones, an issue very often strongly affecting fractured reservoirs. To argue about the role the fault damage zone can play in a fractured reservoir, we are going to observe in this virtual field trip some interesting outcrops. They are good examples for people involved in a reservoir fracture study, but not familiar with geology. Because fracture system exposed, affected by late-acting process like unloading and weathering, are bound to be different from the fracture system of the reservoir, which are located at several thousand meters burial depth, caution must be utilized with what we can see on outcrops. What is a fault damage zone? A damage zone is the volume of the formed rocks around the fault surface that results from the initiation, propagation, interaction, and build-up of slip along faults. This volume of rock is characterized by the presence of a higher fracture intensity than the surrounding rock. What is the impact of the fault damage zones in fracture reservoirs? Generally, in a reservoir affected by several faults, the impact of the fault damage zone is quite significant. For fractured fields of type 1, as per Nelson classification, so affected by a very poor rock matrix and by a very close fault network, the fault damage zone represents almost the total storage and flow capacity. In fact, the fracture intensity outside the damage zone is too poor and the rock matrix tight. For this reason, the wells in this kind of reservoirs are drilled with the target of crossing the fault damage zones to drain the fracture network with good producers. On the other hand, there are reservoirs of type 3, as per Nelson classification, so affected by a quite good rock matrix, for which the fault damage zone represents a risk, because they represent the main way for the water influx from the bottom or gas influx from the top in the oil fields with gas cap. In this kind of reservoirs, the wells are drilled with the target of stay away from the fault damage zone, in order to optimize the recovery from the good rock matrix. It is clear that for this kind of reservoirs, the knowledge of the extension and characteristics of the fault damage zone is very important to quantify the impact of the fracture network and to optimize the location of the wells. During my working life, I spent more than 2 years in Scotland, in Aberdeen, working on the North Sea oil and gas fields. I had then the opportunity to visit and observe several Scottish outcrops, geologically very interesting. Among the others, I think that one of these outcrops can be very exemplary of the fault damage zone. So, let's go to the Lake of Moray area, north of Elgin. Here, we find aeolian and fluvial sandstone created in desert environments, the Devonian Old Red Sandstone and the Permian and the Triassic New Red Sandstone. In particular, let's go to the Cove Bay. Here, we can observe the Clashach faults. These faults, subparallel to the shore, affect both the bay edges, westward and eastward, where we are going to focus the attention. Don't be fooled by the gorgeous day of this image. Actually, a very rare condition for the Scottish seashore, usually affected by a completely different weather: windy, foggy, cold, with the stormy waves crashing on the coast. It is just the outcrop of a normal fault, with the footwall located northward and the hanging wall southward. This outcrop allows us to observe the different elements linked to this structural event. The fault plane affected by slick-side structures. The fault core that generally represent a permeability barrier, being affected by cataclysmicity or breaches because of the slip along the fault plane, which transform part of the zone characterized by the original maximum fracture intensity, F0, in a rock with a very low permeability. Actually, just a few centimeters of rock that represent a sealing barrier to the flow. But just moving away from the core zone, we can recognize the presence of high fracture intensity and deformation bands. Then, moving away from the fault plane, a high fracture intensity can be observed. It progressively decreases moving far from the fault plane, as highlighted by these images. So, a fracture intensity that decreases gradually moving away from the fault plane. We can summarize that fracture intensity is higher near faults because of fault-related discontinuities. However, the fault zone can be regarded as consisting of a central core with a poor permeability, surrounded by a damaged band where the fracture intensity is higher than the hosting rock. The fracture intensity then gradually decreases with distance from the fault wall. So, we could envisage to predict fracture intensity in a faulted area by using the distance from the fault plane. So the question is, can some general rules about the fault damage zone characteristics be inferred from the observation of the outcrops? Many papers have investigated this subject, and some of them are listed in the references. In fact, there are several views and different conclusions have been drawn. However, some general simple indication can be inferred. The first issues to be addressed is what are the models of damage growth around the fault zone. In fact, the fault development is a key issue for the identification of the mechanical processes responsible for the origin of off-fault damage. In fact, fracture damage surrounding fault is likely created by various, sometimes cumulative, processes during fault formation. For example, the Andersonian model that assumes fault formation through the interaction and coalescence of many tensile microcracks. The TIP model that is based on the fault growing by tip propagation where microfractures form. The interaction of multiple fault tips model, where extension fractures formed at the tips of separate individual faults interacting with each other. The fracturing for wear along wavy frictional fault surfaces. However, the generation of off-fault damage zone can be schematically described as a migrating process during fault formation. So, the fault plane growing by tip propagation. With the fault plane increasing displacement. The relevant fault damage zone width, with the fracture intensity decreasing moving away from the fault plane. The fault damage zone width decreasing with the decreasing of the fault displacement. Here we have on the left a graph extracted from a paper of Mitchell and Faulkner. It shows the fracture density versus the perpendicular distance from the fault core of three faults located in the same geological context. They have a well-defined exponential decrease with distance from the fault core. The slope of this trend is quite different because these three faults are characterized by different displacement that is mirrored in the different damage zone width estimated at the intersection with the background fracture density. So, damage zone width scale with the fault displacement, although damage zone width appear to grow more slowly at higher displacement. Moreover, we see that the presence of subsidiary faults have a clear effect on the fracture density and are ignored for the estimation of the least square best fit lines of the master faults. So, the presence of subsidiary faults are bound to introduce a kind of noise in the master fault fracture intensity exponential decrease. All faults appear to have the about same maximum fracture density, probably achieved at the fault tip just before the fault slip. So, this critical maximum fracture density is located at the fault core damage zone boundary, and it is linked to the mechanical property of the rock defined by lithology, lithification at the diagenetic stage, and the burial condition at the time of the tectonic event. The fault damage zone extension is also affected by the linkage of a system of faults. Four stages are here shown. Isolated segment at time 1, evolving in a soft linked ramp at time 2, passing to an overlapping soft linked segment at time 3, to another linked coalesced fault at time 4. So the fault evolves as a segment that grow, link, and amalgamate to form longer continuous faults. This process has an impact on the width of the damage zone. Here, the sketch on the left shows the expected displacement profile for each time step. This displacement profile highlights the evolution of the gap between the two faults passing from a ramp that is affected by a wide linking damage zone, resulting from the merge of the two damage zones. This zone is characterized by very high fracture intensity with a larger range of fracture orientation. Then the process evolves in a hard-linked coalesced single fold, becoming at the end of the process a sealing barrier inheriting the anomalous wide linking damage zone. So, in the light of these papers, some general concepts about the fault damage zone characteristics can be inferred. Fault consists of a core and associated damage zone affected by fractures. All fractures have a reasonable defined exponential decrease with distance from the fault core if data points in the damage zone around the location of large subsidiary faults are ignored. All faults appear to have a critical fracture density at the fault core damage zone boundary that is independent of displacement. It is linked to the mechanical property of the rock defined by lithology, lithification diagenetic stage, and burial condition at the time of the tectonic event. Damage zone white scale with fault displacement. However, damage zone white appear to grow more slowly with higher displacement. The generation of off-fault damage zone is likely created by various, sometimes cumulative processes during fault formation, envisaged as a migrating process. This process brings to the coalescence of single faults in a larger event affected locally by wide linking damage zone. So let's try to summarize these fault characteristics with this sketch. We have the fault plane growing by tip propagation, the background fracture intensity far from the fault where no displacement occurs, the fault displacement gradually increasing from zero at the tip of the fault to a maximum at about the center of the fault, the maximum fracture intensity close to the fault plane, the fracture intensity decreasing moving away from the fault plane, the fault damage zone white scaling with the fault displacement, the perpendicular distance to fault. As illustrated by the plot, the fracture intensity decreases exponentially with the distance to the fault from the maximum fracture intensity. The steepness of this exponential trend is scaling with the fault displacement. That means very steep for small displacement and gradually less steep for larger displacement. How the fracture intensity decline with the fault displacement is unknown. However, as illustrated by the plot on the right, a decreasing trend is expected as the damage zone white appear to grow more slowly with higher displacement. In fact, well data coming from image logs and cores can be very useful to try to calibrate these two plots. We can try to define the maximum fracture intensity close to the fault plane, the background fracture intensity far from the fault where no displacement occurs, the fracture intensity decreasing moving away from the fault plane for the different fault displacement, the fault damage zone white where the decreasing trend crosses the estimated background fracture intensity. Also the effect of subsidiary faults or wide linking damage zone perturbating the master fault fracture intensity decline can be recognized. In fact, the tuning of these two plots with the well data allow to define an equation which describes in 3D the damage zone fracture intensity all around the fault. The requested input are the maximum fracture intensity, the estimated fault displacement along the fault plane, the distance to the fault plane, the parameters A and B describing the relationship between fault displacement and fracture intensity decline, inferable from the plot. This formula, calibrated with well data, can allow us to simulate the fracture intensity all around the fault, a tool that could be utilized to populate a 3D grid model. I wonder if this general concept can be utilized in a reservoir study. The fact that these rules are inferred from a complete different geological context, as the Atacama Fault System, northern Chile, in Granio Diorite, or as the Suez Rift Fault System in Egypt, in tight carbonate rocks, ask the question if these rules are transferable to other geological contexts. Caution is strongly recommended. For example, in the past I wondered if this general concept could be utilized for the fields located in southern Italy, defined as type 1 as per Nelson classification. I've been always quite skeptical about this possibility, although field data highlighted analogies with what is reported in these papers. My view was that only the observation of similar behaviors in an analog could minimize this perplexity. Recently, I had the opportunity of reading a paper published in February 2022 that could represent a good analog for the fields located in southern Italy. The paper illustrates the study performed on the Venere fault, a fault that bounds the intramountain Fucino Basin in central Italy and cross-cut Lower Cretaceous platform carbonate. The work investigates the footwall damage zone of this seismic scale normal fault, characterized by a throw of about 300 meters. A significant portion of the footwall Venere fault damage zone is well exposed in the Santilli quarry, where the observation has been carried out. The fault is studied on two different outcrops, facing each other at the two extremes of the quarry, and represent respectively the area close to the fault, the western wall, and a more distal area in the eastern wall. This fault is characterized by a complex internal architecture because of the presence of several second and third order faults. Here, the western wall, starting southwest from the first order master fault reported in red, and here the eastern wall. The analysis of the fracture network shows an exponential decay of fracture intensity away from the main slip surface, although strongly influenced by subsidiary faults. Observation very similar to those drawn by the other papers mentioned in the former slides. So, considering the observation made on an analog, I wonder if, in a scenario characterized by different fault sets showing different fracture intensity versus distance to fault trend, this approach could be effective handling separately the different fault sets. Of course, the detail of this reconstruction would call for a more grid with an adequate resolution. Here you can find a short list of papers to refer to if you are interested in investigating more in depth the subject.